All right, welcome back. So today we're going to be talking about how to add and subtract within scientific notation. Now, a lot of students are going to say, well, can we just take whatever is written in scientific notation and just put it back into our everyday numbers, or we call it standard form or standard notation? You could, but then the majority of the questions are going to say, please write your answer in scientific notation. So then you went into standard notation to find your answer, and then you got to go back into scientific notation, and you're just doing more work than is necessary. So today we're going to be going through a couple examples on how to add and subtract within scientific notation, and you might find it's going to be a little bit easier for you. So there's three main ideas that I want to establish with you. So the first one is, if the current notations have the same power of 10, then we just add or subtract the terms normally. So for example, if I have, I'll write in blue, if I have like 3 times 10 to the second plus 4.2 times 10 to the second, these have the same power of 10. So we're looking for the power of 10 to be the same. Well, we have 10 to the second and 10 to the second. So we're just going to be adding these terms. And when I say these terms, I mean the ones in green. So the 3 and the 4.2. We're just going to add them normally. Second part is, if notations do not have the same power of 10, then we need to change them into the same power of 10 to then add. And then finally, our answer needs to be in scientific notation. The majority of the time, the answer is going to, or the question is going to say, hey, please write it in scientific notation. So you want to be able to work within scientific notation and do those operations. That way you're doing less work, right? It's not about getting it done. It's about how efficient can we do it, right? So let's go through some examples real quick. So let's just think back to our algebra rules. Can we add 2x and 3x? Yeah, definitely, right? Because they have the same variable. So we get 5x. It's like saying 2 times x plus 3 times x, right? But what about 7x plus 9y? Can we add them? No, right? We can't. No, because they're not like terms. It's 7 times x plus 9 times y. So we would just say, hey, no, they're not like terms. We can't add these. Or we couldn't subtract them if there was a subtraction sign there. But within scientific notation, it's a little bit different because we have the ability to manipulate the power of 10 to get it to be the same exponent in both terms. And we're going to be going through some examples, but this is like the main idea here. If they have the same power of 10, we can add them just like we did with 2x and 3x. If they don't have the same power of 10, then we can't add them, but this time we can't add it initially. We need to manipulate just a little bit. So let's go through some problems here. So I'm just going to scroll down, that way we get all 4. I'm going to ask, oh, wait, no. Let's see. Haha. Can I do it? I got it. Okay, so please pause the video and copy down these 4 problems and give yourself some space here, and then resume when you're ready to listen to the notes. All right, so if you listen to my voice, that means that you have copied down the 4 problems and you are ready to take the notes for today. So let's look at problem number 1. We have 4.9 times 10 to the 5th plus 1.8 times 10 to the 5th. What we want to first look at is see, okay, do we have the same power of 10? So we have 10 to the 5th and 10 to the 5th. Are they the same? You betcha. So that means we're just going to be adding, I'll do it in blue, why not? We're going to be adding 4.9 and 1.8 together. So let's do it. We do 4.9 plus 1.8, and we get 6.7. So we get 6.7. Now, just like we do with our like terms, 2x plus 3x was 5x. We didn't write the x twice. It wasn't x squared. So it's going to be times 10 to the 5th, only once. So we took 4.9 and 1.8 and got us to 6.7. And 10 to the 5th stays how it is. Notice that 6.7 is within scientific notation, so I don't need to change it at all. This is just going to be our final answer. 6.7 times 10 to the fifth. And you can do it in your calculator. If you have a scientific calculator, I'm currently looking at a Texas Instruments, it's a TI-30X. It's more or less the ones that we use in school. If you look above the 7 is a button that looks like this. X to the negative 1, but then above it is this E. That doesn't look like E. Let's try it again. But what that does is that tells the calculator, if you hit that second and then EE, that says I want to the power of blank. So if I were to plug this into my calculator, it would be 4.9, and then that second EE, but when you type it in, it only comes up as 1E, okay? So it only comes up as 1E, and then you would type 5, because it's saying, hey, I want 4.9 times 10 to the power of 5. Then you say plus 1.8, again, EE, but it only shows 1E, 5. This is saying 4.9 times 10 to the fifth plus 1.8 times 10 to the fifth. And then when you plug it in, it's going to give you the number written in standard notation, and you're going to have to go backwards. But this is a good way to check our answer. So let's go on to the next problem over on the right-hand side. So we have 3.85 times 10 to the fourth plus 5.72 times 10 to the fourth. So we want to first check, are the powers of 10 the same? Well, yeah, they're both 10 to the fourth, which is great, right? So that means we're just going to be adding 3.85 and 5.72 together. So let's do it. So we do 3.85 plus 5.72, then we get 9.57. Times, again, now 10 to the fourth. We only write it once, just like when we're combining like terms, we only write that variable once, or the way it is, I should say. So we did 3.85 plus 5.72 to get us to 9.57, and then we carry along that 10 to the fourth power. 9.57 is within scientific notation, so I don't need to convert it at all. So we are super duper. All right, let's go down to these two subtraction problems. Subtraction and addition are very, very, very similar. We need to first see, are the powers of 10 the same? And then if so, we can subtract them normally. If the powers are not the same, we need to convert. And then we always want to have our answer be in scientific notation. So we first want to see with the problem 8.2 times 10 to the fifth minus 4.6 times 10 to the fifth. Are our powers of 10 the same? Yes. We have a 10 to the fifth and a 10 to the fifth. So we can now just subtract 8.2 and 4.6. So when we do that, 8.2 minus 4.6 is going to give us 3.6 times 10 to the fifth. And again, let me just highlight for you. 3.6 came from 8.2 minus 4.6, and 10 to the fifth was the common power of 10. All right, let's move over to the right-hand side now. We have 4.5 times 10 to the negative third minus 1.2 times 10 to the negative third. So we want to see, are our powers of 10 the same? Yes, they are. That's super duper. Now we're just going to do 4.5 minus 1.2. So we do 4.5 minus 1.2. We get 3.3. And we carry along the scientific notation. So we got 3.3 from 4.5 minus 1.2. And now we carry over that 10 to the negative third power. Oh, I never boxed in my answers. There we go. All right, nice job. Let's go on to some challenge problems now. We have 2 challenge problems for you, and we got about 5 minutes to do it. All right, so over on the left-hand side, we have 2.4 times 10 to the third plus 7.1 times 10 to the fourth. So we first want to see, hey, do we have the same powers of 10? Whoa, no we don't. We have 10 to the third and 10 to the fourth. So we can't add right now. We need to manipulate. Here's a big tip for you. Okay? It's easier to change the power to get bigger. So it's easier to raise the power. And here's what I mean by that. I have 10 to the third and 10 to the fourth. I want to raise that 10 to the third. So what I need to do is I need to add 1. Pretty much to the power of 3, right? So that would turn out to be 10 to the fourth. But just like in normal situations, well, we're not doing anything to opposite sides. We have to keep that, we need to keep the value the same. So if we're adding 1 in the exponent, we need to move that decimal once now to the left because we're doing the opposite, right? We add 1 in the exponent, we're going to subtract 1 more or less within the decimal. So now we get 0.24 times 10 to the fourth plus 7.1 times 10 to the fourth. And I know 0.24 is not in scientific notation. It originally was with 10 to the third, but we had to manipulate it a little bit. That way we can operate. And now we have the same powers of 10. It's 10 to the fourth. And now we're going to add 0.24 to 7.1. Then we get 7.34 times 10 to the fourth. And that's our answer. Now notice how we ended up in scientific notation. 7.34 is indeed between 1 and 10, and now we have the same power of 10, okay? So that's why I say it's easier to raise the power up. Let's now go over to the right-hand side, a subtraction problem. We have 4.23 times 10 to the fifth minus 3.5 times 10 to the third. Again, we don't have the same exponent, but it's easier for us to raise power of 3 to the power of 5. So if I add 2 in the exponent, right, I'm increasing by 2 powers of 10. But I need to keep that same value the same. So I have to move this decimal twice to the left. So now we have 4.23 times 10 to the fifth minus 0.035 times 10 to the fifth. And if you plug, let me show you, if we plug this number, 3.5 times 10 to the third, into your calculator, it's going to be the same as this number here. Okay, it's going to be the exact same. So we're not changing the value, we're just changing the way that it looks. So now we can do this actual operation. We can do 4.23 minus 0.035. So we do it in our calculator, 4.23 minus 0.035. And we get, let me switch my pen, 4.195, and we keep the base of 10. So again, we did 4.23 minus 0.035, and we kept that power of 10 for our final answer of 4.195. I'm so proud of you. You're doing so well with this. If you have any questions, please reach out. Keep up the great work, folks. Really, super duper proud of you. Have a good one.